So there's essentially 5 steps in the abstraction process between representing the Earth and making a map. So we start out with the Earth, which is just a lumpy ball of rock careening through space and time. And the first thing we do is we just smooth out the topography and just ignore it. We can incorporate it again later if needed. And that smoothed image or representation is called a geoid. So a geoid is just a smooth, less lumpy ball of rock. And then with that geoid, we can fit a datum to it. So a datum is just an oblate spheroid, and we can fit it to the geoid in a couple different ways, which I'll elaborate on in a minute. But a datum is just fitting a spheroid to that geoid to completely smooth it out. Then we can use a geographic coordinate system to represent locations on that datum. So a geographic coordinate system is just a 3-dimensional coordinate system to represent the location on that datum. And then we can take that geographic coordinate system and we can project it. So we can project the 3-dimensional coordinate onto a 2-dimensional plane, whether it's in a computer screen or a paper map. And so those are the 5 steps, and they're really sort of key to your understanding of how map projections work. So I'll go through each of them in a little bit more detail. So we start out with the Earth. It's just a lumpy ball of rock flying through space, and it's got distortions that cause it to deviate from an idealized sphere. So we've got topography, density differentials, and rotation, right? So it's far too complicated to represent fully, and we need to create abstractions to simplify the shape of the Earth and display it in 2 dimensions, right? So the first step is just ignoring topography, smoothing it out. We can deal with it later if we want. Then we can estimate the geoid. And so this is a simplification of the Earth that smooths away topography, but accounts for the gravity differences. And so the way this is actually measured is by satellites flying around the Earth, and the slight deviations in the satellite's orbit will be influenced by the slight differences in gravity depending on where the satellites are. And so then you can model the differences in the land and ocean surface heights, which again deviate by about 180 meters or so, depending on where you are. And so that can then be used as a reference point to fit an ellipse. So a datum is just a way of linking that ellipsoid to the geoid, right? So it's going to be used as essentially a connection to link the coordinates to the Earth's surface. And so an ellipsoid can be fit to a geoid in basically 2 different ways. We can have a local or a global datum. And so local versus global just denotes where the reference point is for fitting the geoid. So a global datum, the one you see on the right, uses the center of the Earth as the reference point to fit to this geoid. And so the goal of a global datum is to minimize inaccuracy over the entirety of the Earth. But the downside is that it's impossible to perfectly fit an ellipsoid to the geoid anywhere. So you end up with more inaccuracy in more places, but less inaccuracy overall. The other option is a local geoid, or a local datum. And so this fits the geoid very well in a particular region. And this method is used for local scale and continental scale map projection. So for instance, an example would be the North American datum, which was initially created in 1983. That's a common one that we'll work with. And so this geoid is optimized for North America. It minimizes the distortions or deviations of the ellipsoid from the geoid in North America. But if you're on the other side of the world in, say, New Zealand, you have much more distortion. So local datums are great for looking at specific areas. Global datums are better for working with the whole world. And then once you've got a datum, that ellipse, fit to the Earth, you can represent locations on that datum using a geographic coordinate system. So the most common one is latitude and longitude. Essentially, you can think of geographic coordinate system and latitude and longitude being synonymous. So geographic coordinate system is just a system for identifying locations on the surface of the Earth. So all geographic coordinate systems contain an ellipsoid, and all coordinate systems reference to a specific datum. So latitude and longitude is a method for representing the location on the surface of the Earth, but latitude and longitude can be linked to different datums. So for instance, you can have the North American datum 1984 and latitude and longitude linked to that. Or you could have a global datum like the World Geodetic System 1984 and latitude and longitude linked to that. And again, kind of an abstract concept, but basically the key points to remember are the local versus the global datum. Each one can have latitude and longitude linked to it and used to represent the location on the surface of that datum. So I'm sure you've all heard of latitude and longitude before. They're talked about quite a bit, used a lot in geography. Essentially, they are angular measurements, measurements of degrees, latitude and longitude, that are defined by their angular distance from the center of the ellipsoid relative to either the equator or the prime meridian. So for longitude, that's the long ones running north-south. They are defined by their angular distance from the prime meridian, which you can see right here. The prime meridian is just an arbitrary line that was drawn through Greenwich, England, a couple hundred years ago because it was chosen quite arbitrarily because at the time Europeans thought they were the center of the world. Specifically, London thought it was the center of the world. So they drew a line through and they've just stuck with it ever since. It's really an arbitrary choice. Don't think anything to it more than that. Latitude, the lateral ones running north-south, are the angular distance relative to the equator. And so the equator is much more physically rooted logical choice because it essentially splits the Earth into two halves and represents where the Earth is at its widest. And so latitude is the angular distance north or south of the equator. So degrees of latitude and longitude, again, are just defined by their angle relative to the center of the ellipsoid. So latitude can range plus or minus 90 degrees north or south, whereas longitude can range plus or minus 180 degrees east or west. And so a really important thing to note is that the distance between 1 degree of longitude varies drastically based on where you are on the surface of the globe. So at the equator, the distance between degrees of longitude are 111.32 kilometers. But at 60 degrees north, it's only 55.8. And then at the north and south poles at 0, all of the lines of latitude and longitude converge to one another, right? So that's a really important thing to note. It's important to be cognizant of that. I'll explain why that's important when we get further into the discussion on actual map projections. Now, the distance between lines of latitude also changes with distance from the equator as you go north or south, but by a much smaller degree, so we don't need to focus on that right now. So geographic coordinate system serves as the basis for projecting the three-dimensional Earth onto a two-dimensional plane, that plane being a paper map or a computer screen. So I've covered the first 4 steps of the process of abstraction, going from the Earth to a geoid to a datum, and then linking that geographic coordinate system to the datum. And now I'll go on and talk about in more depth the projected coordinate system, how we project the Earth into 2 dimensions.